Hi everyone, it is Ben, a postdoc from UNH and supervised by Professor Noy Lugas. Here I would like to introduce our recent work. It is about understanding the properties of deformed magnetic clouds by numerical simulations and fitting techniques. Let's move directly to the information about CMEs and magnetic clouds. We know that magnetic clouds are the interplanetary counterparts of coronal mass ejections, and they have been studied widely since first identified by Berger in 1981. In this figure, you can see the in situ observations of a magnetic cloud. And magnetic clouds usually have three observational characteristics, which are the enhanced magnetic field strength, the smooth rotation of the magnetic field vector, and the lower potent temperature. Magnetic clouds are very important in the space science studies because they can help with understanding the evolution of CMEs from the Sun to the heliosphere and the associated geo-effectiveness. Today, our knowledge of magnetic clouds is mostly from in situ 1D observation. To derive the information of magnetic clouds in 2D or even 3D, various fitting models have been developed, and these models are mostly based on the idea that magnetic clouds usually have flux-rope structures. And here I will introduce some recently developed models. For example, Hidalgo improved their previous non-force-free flux-rope model. Neves Chinchilla developed their model, which can provide the electric current and thermal information inside magnetic clouds. One improved the previous cylindrical force-free model by considering the velocities inside magnetic clouds. And finally, who improved their Grad-Schaffenov reconstruction with toroidal flux ropes. Here I would like to recommend one recent review paper for you. It introduced the recent researches about Earth affecting solar transit, which contains CMEs and magnetic clouds. All of these fittings extend our understanding about magnetic clouds, and among them, the cylindrical model are very popular. Then there will lead to a question. Let me describe it. Many studies have found that CME will experience the so-called pancaking effect during their propagation. This is due to the interaction between CMEs and the solar wind medium. And the CME cross-section will vary from an initially circular one to an ellipse or even concave shape. Then we're considering that if we keep using a cylindrical model to fit the in situ data from a deformed or pancaked CMEs, what will happen? Does the information have influence on the fit? To solve this question, and it is our motivation. One solution is combining the field and the numerical simulations because simulations can provide the exact magnetic cloud information. There have been few studies using simulations and the field to explore the magnetic cloud properties. In this work, we mainly focus on the information of magnetic fluxes because we know that they are conserved in the ideal MHD frame and they can act as a bridge linking the CME properties from the Sun to the heliosphere. Let me introduce our simulation method. We take spherical coordinates and perform a 2.5-dimensional ideal MHD simulations in the heliospheric meridional plane. What is a 2.5-dimensional simulation? It means that all the physical quantities in the simulations have three direction vectors, but the partial derivative in one direction equals to 0. Here, these are our MHD equations, and we just need to know two things. First is that the polytropic process provides the heat in the simulation, and the second is the magnetic field is described by a magnetic flux function in the meridian plane and the magnetic field vector perpendicular to this plane. We performed our simulations as follows. At first, we construct a solar wind background, and then we insert a flux shock to the solar surface. And finally, the eruption is triggered by the catastrophe of the flux shock system. This movie shows the eruption of the flux shock, in which we found that the cross-section of the flux shock becomes flattened during its propagation. The flux shock boundary is marked by the red curves, and it can be precisely determined by the flux function I introduced before. We calculate the related aspect ratio. This aspect ratio is derived by the radial length divides the azimuthal length, or we can say horizontal length. And we can see that the aspect ratio could reach around 2 during the flux shock propagation in this case. We then set 10 spacecraft at 5 different distances and along 2 angles, and we generate 10 groups of in situ synthetic observations. This figure shows a case of the in situ data at 1U and along 0 degree. And we can find the 3 characteristics of the magnetic clouds here: the enhanced magnetic field, the rotation of the field direction, and the reduced proton temperature. We then use the velocity modified cylindrical model to fit the in situ data. This model has 2 descriptions. One is the linear force-free field with Lundquist solution, and the other one is the nonlinear force-free magnetic field with Gold and Hoyle model. And in this figure, it shows the fitted results compared to the simulations. And we can see that the fields are quite consistent with the observations of the simulations, while the Lundquist solution gives a better fit, the red one. We then performed the fit to all the 10 cases, and then compare the fitted parameters with those derived by the simulations. These parameters contain the radius, the magnetic field strength, the direction of the magnetic cloud axis, and the axial and colloidal magnetic fluxes. And based on this figure, we have a few findings. First, we note that the fits are not always consistent with the simulations. Although the root mean square values agree with the good fit results and below 0.0. Second, fit with Lundquist solution and along 0 degree match better with the simulations. And the third, now we have the Lundquist solution, we have 0 degree. And if we only focus on these data points, we can see that the fit underestimates the axial magnetic flux, and the more flattened the magnetic cloud is, the more underestimation there will be. Last, the flattening has very weak influence on the fit of colloidal flux. The previous result reminds us to carefully use the cylindrical model when studying the in situ magnetic clouds. The underestimation can be understood in this way. When a deformed CME passes a spacecraft, this is a deformed CME, and we use the cylindrical model to fit it, then we will just consider it in a circular region, and this outer part will be ignored. Thus, we can't avoid missing the axial magnetic flux in this part. However, as for the poloid fluxes, they are conserved along this line, from this line to this line, and that it won't be influenced by the deformation. We also make another simple comparison. We calculate the axial and poloid fluxes by inputting the radius and the magnetic field strength from physics and simulations into these two questions. These two equations. These equations are derived by the Lundquist solution, and this figure shows the result. You can see though there are some scatters, but the data points are very close to the unity. We calculate the axial magnetic flux inside the inner circular region in the simulations, and their percentages relative to the total values are shown in this figure. It shows that both in the simulations and the fields, the axial flux is underestimated. Or we can say that in the inner circular region, it only contains a part of the axial magnetic flux. So finally, the summary. In general, we use numerical simulations to study the influence of the CME deformation on the in-situ fitting techniques by cylindrical models, which may help us with further understanding about deriving the magnetic cloud information. And thank you.